Alright, so today we want to look at separable word problems. So we're going to apply what we learned about separable differential equations in the last video to applicable word problems that we can study in the natural sciences mostly, but this can come in other places as well. Whenever you really have a rate, you can be dealing with a separable word problem. We're going to be doing two now, and then we've also got our problem set where you can find more. Let's get started. So the first is for kinetics. So kinetics is a topic that you learn in chemistry, and this is about when you have a reaction where you go from reactants to products. And in our case, we're not going to get very in-depth into it. We're just going to be going from one set of reactants to one set of products, or one reactant to one product. What you deal with is you deal with the concentration of one of them to the concentration in the other one, and you want to think about how fast these concentrations are shifting. So the rates. So you want to look at the rate of A and the rate of B. And I should note, we're going to use the convention where we're going to drop these little square brackets just because we need to write them too many times. We don't want to do that. So we're just going to be writing A and B, although that might be in the concentration of A or the concentration of B. Okay, so what we want to do is we want to derive the rate law for a first order reaction. Okay, or we want to find the integrated rate law for it. We can find the rate law, that's pretty easy. So the rate law will give to you. So the rate law is this guy, dA dt equals Ka. Okay, that's pretty easy. But now we want to find this in terms of something that isn't calculus. So, right, so we want to get rid of the derivative. So what we want to do, so we want to take dt and multiply that by both sides. Then we're going to divide a by both sides. What we're going to get is we're going to get some sort of expression that looks like d over dA over A, or d concentration of A over concentration of A, equals negative K dt. Of course, what we're going to do is we're going to integrate that, and these are both very easy integrals. But we also need to find our bounds, so we're going to go between we're going to set these arbitrary bounds. We're going to go between an initial concentration in A to final concentration in A, so we're going between A naught and A. We're integrating dA over A, and then that's equal to negative K, the rate constant, times the integral between some initial time 0 and some final time t, just integrating dt. Now, of course, that's pretty easy. Of course, we just get the natural log here. And, of course, we can apply the rule that says natural log of y minus natural log of x equals natural log of y over x. We can apply that rule, and we get the natural log of A over A naught is equal to negative KT, which is, of course, our first order rate law, or first order integrated rate law. So we should see we did do an integral there. All right, let's move on to a slightly more involved problem. I'm going to look at resistive forces. So this is something that you come across in your classical mechanics class. Now for this problem set, I really need to dive deep into my notes for thermodynamics, kinetics, and elementary classical mechanics to find these problems. But anyways, we're going to be dealing with a resistive force. So this is going to be an arbitrary resistive force. I'm going to define everything for you, so we don't need to worry about any of the physical stuff, but the mathematical stuff we're going to be covering. Okay, so we're going to start with just our statement. So a resistive force is equal to some negative beta times v squared. And beta has the units of kilograms over meters for SI units. Okay, so we can draw our free body diagram. So we have our we have our little object there. We have, of course, mg pointing us down, right? And then we also have our resistive force pointing us up. This is working against the velocity, negative v squared. We're working against the velocity. We can also define a coordinate system. We're gonna define a coordinate system. We only need one coordinate. we're going to define this the j-hat coordinate system. But we don't really need to worry about that. All we need to worry about is that our variable of interest is v. So we need to deal with this Newton diagram and synthesize this with F equals ma. I, of course, prefer the Euler-Lagrange method, but that's for a later time. Anyways, let's synthesize this. So we know the Newton's law, F equals ma. So we need to synthesize this. So we know what ma is. We do know how to sum all of these forces, of course. So F equals ma. So this means that mg minus bv squared is equal to ma, m dv dt. So we're summing our forces, and we're setting them equal to ma, which is, of course, the derivative of velocity. But velocity is the variable we're working with, so we're going to write that as the derivative of velocity instead of just a. Okay, so we can rewrite this. We can take out an m, and we are going to get dv dt is equal to g minus b v squared over m. Okay, so now you can see where we're going with this. This looks like a separable differential equation in time and in velocity. So you can kind of see how we're going to need to manipulate this, and then we're going to need to integrate. Now this is going to be a lot more involved than some of the other ones that we've been dealing with, of course. Okay, so let's work on this. So for this, we are going to want to rearrange this so that it's a little bit better for us. So we are going to divide everything by g minus bv squared over m, and then multiply everything by dt. So we get dv over g minus beta v squared over m is equal to dt. Now we're also going to take a g out of this denominator, and we're going to multiply everything by -1. So we get negative dv over g times 1 minus beta v squared over mg is equal to negative dt. All right, so now we're going to multiply everything by g, and then the g is going to go over to the dt side. So we're going to get negative dv over 1 minus beta v squared over mg is equal to negative g dt. Okay, so now what we're going to want to do is we're going to want to make a substitution. And this is going to make our life easier so that we don't need to deal with all these crazy little integrals, right? So let's deal with that. So we're going to set u equal to the square root of beta over mg times v. And of course, you differentiate, the v goes to the dv for du. So we are going to get, sorry, this should be a times symbol. That's not an equal symbol. We get a square root of mg over beta times the integral between 0 and some function u of t, which we'll deal with later, of du over 1 minus u squared is equal to negative g integral dt. Okay, so again, we have some easy integrals to deal with, and what we are going to end up with is an equation of motion that says that 1 minus the square root of beta over mg times v is equal to 1 plus beta, the square root of beta over mg times v times the exponential, so that's the equivalent of e to the blank. But when you have big arguments for the exponential, it's nice just to write exp and then have nice big parentheses to put everything. Exponential of negative 2g square root of beta over mg times t. All right, so there's our equation of motion that we want to be dealing with. So that is how you kind of look at a differential equation in terms of this Newtonian physics problem. All right, in the next video, we're going to be back and we're going to be talking about exponential growth. We'll see you then. Bye.